Hi, everybody. This is like my seventh recording of this, so maybe this time I'll get it right. As you can see my face. I paid $30 so you guys could see my face, FYI. Um, so what we're going to do is this is screencast number 2. I'm going to do another screencast on all the changes to the AP exam because I'm still trying to wrap my head around all of that. Moral of the story is no multiple choice. It's only FRQ, and if you want 100% refund for it, you can get 100% refund for it. Okay. And then half-lives you guys had some issues with. So what I'm going to do is I'm going to go through, I'm going to look either for another video explaining how to do it, or I'll make you guys a tutorial for it. Okay. So I just want to review with you nuclear fission. So you have fusion, which is 2 coming together, and then fission is splitting 2 apart. So here is a nice little animation about how this process of nuclear fission actually creates energy to essentially boil the water, to create the steam, to turn the turbine, to turn the generator that generates electricity. So here we go. Nuclear reactor, you have these fuel rods. They have the uranium that has been enriched to 3%, which is way more than is found in nature. And what happens is why isn't this working? There we go. We throw neutrons at this uranium and it becomes really unstable. And what it does is it then splits into 2 daughter nuclei. Here it's barium and krypton, and it creates 3 more neutrons. Those neutrons can then go on and hit more uraniums and split them. It's not even exponential growth, it's more, because every one that splits, it creates these 2 daughter cells, but then it also releases 3 neutrons, which can then go and hit other ones. So we're kind of seeing that with corona right now. You can infect a certain number of people and you get more than exponential growth. Oh, here we go. So anatomy of a nuclear power plant. You have the reactor building, the powerhouse, and the cooling tower. Those are the 3 main sections. So going to the reactor building, this is where you have where you would have your coal, your oil, or your natural gas to boil the water to create the steam. That's what happens here. So you have enriched uranium rods, and then you have so those are the fuel rods, and then you have these control rods in the middle. These are the gray ones that are the control rods. And what the control, here we go, shielded reactor core, rods of nuclear fuel, and here are the control rods. What the control rods do is they absorb neutrons, so they can control the rate of nuclear fission. They can't stop it, but what they can do is they can absorb a lot of the neutrons so that you don't have the rate happening as fast. Okay, social distancing. So what happens here is that you have a water pump which needs to constantly circulate water through, because if you have one spot getting too hot, what happens is steam under pressure or water under pressure, it can become too hot and melt down. And that's what we saw happen in Fukushima. What the water pumps were taken out by the tsunami, and you had meltdown in the reactor core because that nuclear fuel got too hot. Okay, so here's your heat exchanger, and if you look here, your red and your orange, okay, are all in the. I wonder if I can draw this. There we go. So the red here is really super hot, and the orange here isn't very hot. So it comes through, and it's a heat exchanger. There we go. So the only water or liquid metal that is touching uranium is in this first loop. Okay, and we're going to learn about what type of reactor core this is. The powerhouse is where the steam produced from the heat exchanger and the reactor, it drives the steam turbines in the powerhouse. So here you go, you have the steam turbine. So you have the steam coming in from here. It turns the turbines, it goes down, and this blue here is cold water. Okay, and that cold water condenses, this whole thing is called a condenser. It condenses the steam back into water, and then the water gets fed back into the reactor core. Okay, So your generator generates the electricity. You have your cooling tower, which cools the water. And again, you have water pumps constantly circulating this water through, so nothing gets too cold, nothing gets too hot. Like a giant Goldilocks in here. Okay, and there you go. There's your condenser. There's the steam, and there's the cold water. Uh-oh. All right. So how is fission used in a nuclear power station? I know you guys all know you boil the water to create the steam to turn the turbine, but what this is it's a nice little, it shows you how it's done. So stage one in the reactor, nuclear fission in the uranium fuel rods releases heat, which is used to boil water. So you see the boiler right here is now boiling water. Boiling water produces high pressure steam. The force of the moving steam turns the turbines. The turbines turn the generator, and electricity is produced. Okay, then that steam goes up through the cooling towers. It condenses back into water, and it goes back into the boiler. Okay, here they show it as a single loop. Uh-oh. How do I get to the next page? Oh, there we go. All right, so here, the thing is that I want you guys to know that I like this image because it's three different colors. You have inside your containment building, you have this first loop, which is just orange. Okay, and if you notice, all of the water or metal or whatever it is that's used to become very heated is self-contained in that area. And then here you have the steam generator. Oh, there we go. That goes through the turbine, and that steam comes back through the condenser. So you have cold water, which is this green behind it, and you have this blue here in the second loop. Those waters never touch each other. They're in different pipes, okay? And then here you have your condenser, which is your third loop. And again, the condenser water never touches the steam, okay, in that area. And that's really important. I put this image on your study guide. And if we were in class, what I would have you guys do is actually draw these three different loops. Okay, you see A here is your first loop, your C and your D. Here we go. So your A is your first one. There we go. Oh, it is terrible to draw on this thing. Okay, so here's your first loop. Okay, your second loop would be, here we go, some green. Your steam coming up through here into the turbine, okay, down through the condenser, and then back in through here, okay, and all in this background here. And then your third loop would be, let's go dark blue. Here in the background is your cold water, okay, coming in from your cooling tower. Okay, so one of the questions is to identify A, B, C, D, E, and F. All right, so we have heavy water reactors and light water reactors. I don't know that you're honestly going to have to know this, but your heavy water reactors um, don't use water. They use something like a metal, deuterium oxide, as its coolant and its moderator. Okay, it's kept under pressure. It can go to extreme high temperatures without boiling because it's under pressure. You remember PV equals nRT, ooh, physics. And it's really, really, really expensive, so we don't use it a lot. What we're going to focus on are light water reactors. It uses normal water, and we have two different types. You have a pressurized water reactor and a boiling water reactor. Okay, so pressurized water reactor is the water's pressurized. Boiling water, you actually have that water that boils. Okay, and here you go. So your pressurized water reactor has three loops. So you see this red here, and then you see the blue, and then you see the other blue. Whereas your boiling water reactor has two loops, just like your B. Okay, so if you guys were Leo, and I'm going to draw a B for you here. There we go. Oh, this is terrible. There we go. If I were drawing a normal B, your B has two loops. So that's a really easy way to remember that your boiling water reactor has two loops, your pressurized water reactor has three loops. So if you look at this picture, is it a pressure water reactor or boiling water reactor? Does it have one or two loops? Okay. So here you've got one loop all through here. Whoa. And then you have your second loop, change the color, through here. This is your cooling tower. So it's got 2 loops. It's a boiling water reactor. Here, you have a pressurized water reactor. You've got your 3 different loops. How about this one? Take a look at it. How many loops? Oh, there we go. 3 loops. So it's a pressurized water reactor. With this one, already color-coded for you, 2 loops, boiling water reactor. Okay. And same thing here. This is 1 loop. Okay, so you've got your steam coming up through here, going through your condenser and back down. There's a pump again, going back into the reactor core. So that's 1 loop and your second loop there. So you've got a boiling water reactor. Okay, so moving on to the nuclear fuel cycle, what you have to do first is mine the uranium, process the uranium, as you guys already know, to that 3% number. You use it in the reactor. And then at some point in time, it's not useful anymore. It's not going to boil enough water. And so what you need to do now is you need to store this radioactive waste. Uranium has a half-life of like 24,000 years. So you have to store this for like 24,000 years. It's still dangerous in the environment. And just like they did with or they are doing right now with the Oyster Creek nuclear power plant, you have to decommission that reactor because so many of those internal parts are now radioactive. All right. A lot of advantages of nuclear power generation. We have a lot of uranium and we have a lot of domestic supply of uranium, and you don't need a lot of fuel for it. Okay. The comparison to coal, oil, and even natural gas, you need a very small amount of uranium and it produces a lot of energy. There are very few direct environmental impacts unless things really go wrong. There's low carbon dioxide emissions for when it's actually running. But the thing is mining the uranium out and enriching them does actually take fossil fuels. So it's not zero carbon dioxide. They're very safe. But when things do go wrong, they go really, really wrong. And it takes thousands of years to clean up. Okay. It's less of an immediate environmental impact compared to fossil fuels, but there's a huge long term. And it's a carbon free source within the nuclear power plant itself. Okay, so no greenhouse gases are emitted to generate this type of electricity. However, there are fossil fuels that are used in the mining, the enriching, the transporting, etc. Okay, few air pollutants and no carbon dioxide emissions, no smog, no soot. So environmentalists are kind of split on nuclear power. You either like it for the interim of your solar energy and all of your different renewables because we don't have the battery storage, as you guys remember seeing in that video that we watched, the Nova documentary. Okay? And then you have disadvantages. Really expensive, very high startup costs. The chance of catastrophic environmental damage if an accident occurs is overwhelming. And we don't have a good, safe storage solution for all of this spent fuel. So the Gates Foundation, Bill and Melinda Gates, have been working for years on creating a nuclear power plant that runs on spent nuclear fuel that we can't use to generate electricity anymore. There's just not enough left to boil that water. Okay? Decommissioning old plants presents a lot of different waste problems. Technology can be adapted to produce nuclear weapons, which is why we don't want North Korea to have any nuclear power plants because then they can use their spent fuel to create nuclear weapons. It generates a lot of radioactive waste, and most of that is stored on site. The Oyster Creek nuclear power plant, it's being decommissioned, but all of that spent nuclear fuel from the oldest operating nuclear power plant, you're talking 1969, that thing's been generating waste for, and there's no place to put it. So it's being stored on site. So instead of now being a nuclear power plant, it's a spent nuclear fuel storage area, and it still needs to be monitored. So many of these steps require fossil fuels like mining and disposal. You do create thermal pollution, as we studied in the water pollution unit. Oh, and that's it. So you guys can go ahead and answer those study guide questions. And as always, um, the new norm is upload them in the Google form. Okay. So whatever questions that you guys have, I'm also going to include a question on the bottom saying, what do you need? What do you need more of? And I'll do my best to do some sort of like a Q&A with you guys. All right. Stay safe, social distance, stop hanging out with each other, and we'll get through this.
Stay classy, San Diego. San Diego.
I don't even know how to stop this.
San Diego.
No.
We got a substation.
I don't know where my annotations went. I'm still recording.
I've been all through that nuclear plant.